Hi, I am Jiří Smutka, and today I'm excited to introduce our new evaluation board, which we are going to use to test the third generation ST silicon carbide MOSFETs. It is always very important for designers to be able to obtain real data about the switching devices they want to use in the real application context to prevent issues in their final design. This specific platform is designed for testing HIP247 for lead devices, especially silicon carbide MOSFETs in half-bridge configuration. This board can work in different modes, including buck or boost conversion. It has a small heatsink that allows a maximum power range from a few hundred watts up to a few kilowatts, depending on the device you use and the operating conditions. One of the key features of this board is the ability to test the switching performance of active or passive switches. We can measure the switching energies of the transistor and monitor the waveforms of the drain source voltage, source current, and gate source voltage. We can also measure the impact of external conditions like the gate resistance, external gate source capacitance, and driver features like active Miller clamp. It is extremely important to understand the fundamental behavior of all of these parameters to be able to optimize the design phases of the final application. With this board, you can easily test the performance of your silicon carbide MOSFETs in half-bridge architecture. You can evaluate their switching performance and measure the impact of external conditions, allowing you to optimize your design for maximum efficiency. Before we continue, I want to stress the importance of the safety when working with this evaluation board. This video is for demonstration purpose only. Please refer to user manual 3044 on st.com for full safety guidelines. This board is designed to be tested in a laboratory setting, and the operator needs to understand the possible risk involved. The applied high voltage rail can reach up to 1 kilowatt once the power source is connected. So you need to be extremely careful not to touch any points on the board while it's powered. You should place the board and external equipment behind a protection shield to avoid any injury. You should follow these steps when testing the board in unknown condition. First, apply the control signals, then the driver section DC supply, and check if the gate signals are operating properly. Then, apply high voltage step by step from 0 to the set voltage and keep checking the waveforms, mainly drain source and gate source. It is important to check that the signals are not approaching the absolute maximum rating of the tested device. Now, let's take a closer look at the evaluation board and its basic terminals. To make it easier to understand, we will show the schematic and related components on the board in parallel. There are two active silicon carbide MOSFETs in HIP247 for lead packages on the board. There is also a STGAP2 isolated gate driver on each subboard driving the MOSFETs, and there are two auxiliary SMPS based on the L6986I chip to supply the gate side of the board with the gate drivers. Regarding the board connections in the low voltage and low power area, there is a 4-pin jumper connector for the DC supply of the drivers and signals for the driver inputs. If the signal is left open, the driver keeps the output low, which is useful when the board is controlled by an external MCU board. You can also connect the supply voltage using a screw terminal, and there are two SMA connectors for signal inputs when using an external generator. Now let's take a look at the board power terminals. As you can see, we have already connected the necessary parts to demonstrate how the board works. The board contains 6 power terminals, J1 to J6. These terminals can be connected by an M4 screw. Your connecting cables must have appropriate terminals. Terminals J3 and J4 are for connecting an external inductor with appropriate current and inductance for your intended test. Terminals J1 and J2 and J5 and J6 are connected to input and output foil capacitors. These terminals are used to connect the high voltage power supply and the load if the board is tested in power mode. Terminals J1 and J5 are connected to ground. For buck mode operation, terminals J1 and J2 connect the input voltage, and J5 and J6 connect the load. In boost mode operation, the connections are opposite. So J1 and J2 for the output, and J5 and J6 for the input. Another important feature of this evaluation board is the ability to measure signals during a double pass test. Let's see how it works. You can measure the currents through the low-side MOSFET source in two ways. The first way is by using this low inductance surface-mounted sense resistor R22 with frequency compensation. In this case, the signal is connected with the MMCX connector. The second way is by applying a coaxial shunt R13 to the available mounting hole. For testing, we recommend the SSDN414 series coaxial shunt to ensure enough bandwidth for the detailed MOSFET current waveform. To use a coaxial shunt, you need to remove resistor R22. You can measure the energy of the active switch controlled by the gate signal or the energy of the passive switch. To test the active switch, J2 and J6 must be connected by the external clamp. The DC voltage is connected to J6 positive and J5 negative. The energy during transients is measured on the low-side switch Q2. This switch is actively controlled by an external signal, and the high-side switch Q1 is turned off by keeping the control signal low. You can see the drain source voltage shown in the blue wave and the source currents through the active switch in green. The product of the drain source voltage and the source current is shown in orange. It gives the power losses generated in the low-side MOSFET and can be used for energy calculations. You can also see the waveform of the low-side switch gate and check that the signal is safely below absolute maximum rating. The gate signal is displayed in red. To measure the voltage and current on the passive switch, connect terminals J6 and J5 with an external cable, and then connect the testing voltage to J2 positive and J1 negative. The signal for the high-side switch Q1 is a double pass test waveform, while the low-side switch signal is set to low. By using the double pass test feature of the board, you can measure the current and voltage of your silicon carbide MOSFETs in half-bridge configuration. This information is fundamental for optimizing your designs and ensuring maximum efficiency.